Okay, so as we saw in that last example in the previous video, there are times where the seemingly obvious choice of yp leads you to a contradiction. And we identified the source of that. So in that example, our first choice of yp was ax plus b plus c e to the negative 2x. The issue, and I can go back to that page, the issue was that our complementary solution contained a constant and a term of the form constant times e to the negative 2x. This choice of yp includes terms like that. It includes a constant, and it includes a constant times e to the negative 2x. That's what caused the contradiction. So what we need to do in a case like that is use something that we call the multiplication rule. Before we talk about that, I want to break down the kinds of examples that we've seen so far into two cases. The first case is when you choose yp, none of the functions, none of the terms in that yp coincide with the terms that are showing up in your associated homogeneous equation. And again, what I mean by that is if I see a constant here in yp and I also see a constant in my choice of yc, that's what I mean by coincide. Now, case 2 is like the example that we just looked at. The first 4 examples that we looked at across the first 2 videos in this section were all case 1. Case 2 is that 5th example, that one we just looked at. Case 2 is when a function in your assumed particular solution, yp, is also a solution in the associated homogeneous equation. In other words, they have terms in common, or at least the form of those terms are in common. So what do you do in case 2? We just did an example of one of these, but we want kind of a general rule to follow. So first of all, in case 1, the assumed form of yp should be a linear combination of all functions that can be obtained from repeated differentiations of g of x. So this general rule kind of justifies what we did when we, let me find a second example here. Back in the second example, where g of x was cosine of 2x, and repeated differentiations of cosine of 2x are going to produce cosines of 2x and sines of 2x multiplied by some constant. But the important thing is that it produces sines and cosines of 2x. So our choice of yp is a linear combination of cosine of 2x and sine of 2x, right? This general linear combination. That's what this is saying here for that case 1. Case 2, we use this thing that I just mentioned called the multiplication rule. And what this rule says is that if you start with what I guess we could say is the obvious choice of yp for a given g of x, and then if you compare that to your complementary solution, which you should have already found by that point, and if you find any terms in common, like we did in that last example, then what you do is you take the entire expression from which that term came and multiply it by whatever power of x eliminates that overlap between your particular solution and your complementary solution. And here's what I mean by that. So over here, once again, we had a constant in our complementary solution, and in our first choice of yp, there was also a constant. That constant came from the larger expression ax plus b. Because there was that overlap, constant here, we had to multiply by x. But you don't just multiply that constant by x. You have to multiply the entire expression that the constant came from by x, turning that into ax squared and that into bx. Okay, that eliminates the overlap. It may happen in a different example that multiplying only by x doesn't do it. You may need to multiply by x squared or x cubed or some higher power of x. And so the multiplication rule says that you have to multiply that expression by x to the n, where n is the smallest positive integer, which eliminates that overlap. Okay, so let's take a look at another example. This time we're going to do a 4th order differential equation. And because it's 4th order, I am going to actually skip some of the calculus. And I'll mention when I'm doing that. But the reason for that is, well, you'll see pretty quickly. First of all, let's get our auxiliary equation. auxiliary equation in this case is going to be m to the fourth minus m squared equals 0. That factors to m squared times m plus 1, m minus 1 equals 0. And of course, we end up with solutions m equals 0 plus or minus 1. So those three solutions. 0 has a multiplicity of 2. And so we know that when you are going to your complementary solution, we have, that's like case 2 of what we dealt with back in section 4.3. Not this case 2, but the case 2 of the 3 cases we looked at in 4.3. So that's going to generate C1 plus C1, or C2x, okay? Both of these, yes, would have like an e to the 0x, but as we've seen before, that just equals 1, so there's no need to write that. And then from these two guys, plus or minus 1, those factors only showed up once. So I get C3 e to the x plus C4 e to the negative x. So there's my complementary solution. That's fine. Now, what should yp be equal to? Well, before we jump into yp, look at g of x. Look at the function that we use to find inspiration for yp, our particular solution, and compare the terms in this function to the terms of our complementary solution. I have a 4x there. Normally what I would do in a particular solution is I would have to get an entire linear expression, ax plus b, right? But we have, unfortunately, overlap. Not only do I have a constant here where I have a constant here, I also have an x term here and an x term here. Now in this case, multiplying this expression by x is not enough. Because if I multiply everything by x, then this becomes bx, and I still have an x term matching an x term in my complementary solution. So x is not going to do it. But if we multiply by x squared, if I multiply everything by x squared, this becomes ax cubed, and this becomes bx squared. Now I have a cubic term and a quadratic term in an x squared, neither of which show up in my complementary solution. So that took care of that overlap. I keep calling it overlap. Your book doesn't use that term, but that's just my own word for it. Okay? Now let's take a look at the second term here. 2x e to the negative x. Well, we don't really have any issue here. This is a product, first of all. A product of a polynomial, 2x, with an exponential function, e to the negative x. So we use kind of the most general linear expression times e to the negative x in our solution. And there's no issue with that because we don't have any terms that resemble that in our complementary solution. So we don't need to multiply that one by anything. We can just call this plus, I got to use c, not a, c x plus d, general linear expression, because I have a linear expression there, times e to the negative x. Okay? Now you may look at this and say, why did I not multiply by, capital E, e to the negative x? And the reason for that is because that constant that would have appeared there could have been multiplied into these parentheses and turned this c and d into just some other constant anyways. So it's kind of unnecessary and redundant to put another constant in here. This will actually suffice. Here's the reason why I'm going to skip some calculus. Notice that I need 4 derivatives of this thing because I'm looking at a 4th order dE. It's not a 2nd order dE anymore. 4th order. That is a long and tedious process. And part of the reason for that is because one of these terms involves the product rule. So it's going to be a lot of work to generate all of those derivatives. What I am going to do is I am essentially going to cheat. I'm not really cheating because I actually did all of the work myself on my scratch paper that you're not seeing off to the side here. But it's a lot of work. In fact, if you want to see, here's all the work that I had to do to get all 4 of those derivatives. And even then, I'm skipping a lot of algebra, right? So what I'm going to do here is notice that in my dE, I actually only need the 2nd derivative and the 4th derivative. So I'm going to do one of these, dot, dot, dot. What does the 2nd derivative look like? The dot, 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 indicating that I would have found the 1st derivative in here and then moved on to the 2nd derivative. The 2nd derivative, after simplifying everything on my scratch work over there, is going to look like 6ax plus 2b plus, I'm going to have parentheses here, cx squared plus negative 4c plus dx minus 2d times e to the negative x. And that's after simplifying, right? So it's kind of messy. Let's go down a little further. Assume I found the third derivative already, because I did on my scratch work. Now we're down to the fourth derivative. Fourth derivative after simplifying looks like this. Cx squared plus negative 8c plus d x plus 10c minus 4d e to the negative x. Okay? So with that, we have the second and fourth derivative that we needed. We can put those into our dE and then see about solving for those coefficients. So let's do that. Up here, my fourth derivative is this guy right here. That's going to look like cx squared plus negative 8c plus d x plus 10c minus 4d e to the, sorry, that should be negative x up there, e to the negative x. And then minus my second derivative, which is up here, minus 6ax plus 2b plus cx squared plus, where are you? Negative 4c plus d times x minus 2d, regular parenthesis there, e to the negative x. Okay? And that should be equal to my g of x found up here, which is 4x plus 2x e to the negative x. Okay? Looks awful, I know. Which is kind of funny because the original DE looked so innocent, right? It was just two simple little terms over here turned into all this. Simplifying this down, notice, for example, if I distribute the e to the negative x in, I'm going to have a cx squared e to the negative x. I'm going to subtract cx squared e to the negative x. So I actually get some cancellation happening here. A lot of other stuff is going to combine. But what this all kind of filters down to is the following, after all the algebra: negative 4cx plus 10c minus 2d times e to the negative x minus 6ax minus 2b equals 4x plus 2x e to the negative x. Okay? Now, what can we glean from this? Well, first of all, here's an x term. Compare that to this x term, right? 6ax. So 6a needs to equal 4. That implies that a is going to equal, or sorry, that's a negative 6a. I need to include the negative. Negative 6a is going to equal positive 4. That would imply that x is equal to, or sorry, a is equal to negative 2/3. That's what's going to turn that into a 4. So a comes out to negative 2/3. Now let's compare the constant term. Well, I don't see a constant term over here, which means that the constant is actually 0. That means b has to equal 0 so that this constant goes to 0. b equals 0. Now we move over here. Okay? So for this guy, I have negative 4cx plus 10c minus 2d equals 2x. Okay, so I have a linear expression in here in parentheses, and I know that the constant term should equal 0 because there is no constant term showing up over here. It's just 2x times e to the negative x. So now I'm going to equate that 2 to that negative 4c, which means c has to equal negative 1/2. Okay, plug that negative 1/2 in for the c here. That gives me negative 5. I need this negative 2d here to come out to positive 5, so it cancels with this negative 5, making the whole thing 0. The only way that's going to happen is if d is equal to negative 5/2. Yes, I could have set up a bunch of equations and solved them algebraically, but remember, I'm trying to be as efficient as possible and not go through all that algebra here. So now we're in a place to finally wrap this up. my solution is going to be my complementary solution, which we have up here. I'm going to copy it down here. C1 plus C2x plus C3e to the x plus C4e to the negative x. And then, remember, here's what my particular solution looks like with all those coefficients. B, we discovered, was 0. That means that this x squared term is going to drop out on us. So ax cubed is going to look like minus 2/3 x cubed, just bumped my thing there, plus, using these coefficients here, we're going to have negative 1/2 x squared minus 5/2 x e to the negative x. Okay. Oh, I'm sorry. I'm looking at this and I'm realizing that's not right. That doesn't match. I failed to recognize that we actually did need to multiply this guy by x. Why did we need to do that again? Oh, yes, I remember why. So I'm going to go back and make a correction at the very beginning. I had originally said that we do not need to multiply this term by an x because there was no overlap between what we're seeing here and here. The problem is that there actually is. So if I were to take this expression, my cx plus d, and distribute that e to the negative x in. Now what I'm going to have is a constant, my d, times e to the negative x. And notice I actually do have that showing up in my complementary solution, constant times e to the negative x. So I made a mistake there. Rather than reshoot this video, since I'm now 17 minutes in, I'm going to just correct that first step. What I should have done is multiplied this guy by x, giving me cx squared plus dx. Notice that does not, even after distributing this e to the negative x, and that does not duplicate any of the terms in my complementary solution. Now you're saying, but Professor Dale, if you fixed this first step, don't you have to go through and fix everything else? Well, no, because when I go back and I look at my notes, again, this is my scratch work off to the side, I actually remembered to do that in my scratch work. And so all of this work assumed that correct solution there, or that correct expression there. So, haha, I don't have to go redo everything. But, you know, mistakes happen. I'm just glad I caught that one and was able to fix that. So that's why my solution has this x squared and x term in here, because that should have been there all along.